This video demonstrates acoustic source localization by means of a line array using not only direct wavefronts, but also exploiting reflections inside an enclosure. We are in a room of size 6 by 5 meters and a reverberation time of about 700 milliseconds. There are reflective surfaces on the floor, on the walls, while the ceiling is not a regular surface. We use a NIST Mark III array with 64 microphones spaced of 2 centimeters. The array samples the sound field with high spatial resolution along its axis at a sampling frequency of 44.1 kHz. We will use first a controlled acoustic source, that is a PC loudspeaker emitting a time stretch pulse, which is a specific test signal suitable for the measurement of impulse responses. Impulse responses from the loudspeaker to the 64 microphones are estimated and displayed in a graphical representation from which the pattern of wavefronts arriving at the array can be identified. Since the loudspeaker was oriented toward the wall, we have a reflected wavefront with higher amplitude than the direct wavefront. Minor reflections are arriving later. This is the same information displayed according to a color scale from the minimum amplitude to the maximum amplitude, as a function of time and of the linear coordinate along the array. If we apply an ideal model of sound propagation inside the room, according to the image method, we can produce a simulated pattern of low-order reflection, which is shown here in yellow. This is the direct wavefront, this is the reflection on the right wall, this is reflection on the floor, this is reflection on the left wall, while these are second-order reflections. The simulated pattern matches the measured one only if we correctly simulate the size of the room and the position of the source. Some reflections may be weak or may be missing due to the position and the directivity of the source or to the reflection properties of the surfaces. If the position of the source is unknown, we can produce an acoustic map of the room by means of a measure of match between measured and simulated patterns. In this case, we have a two-dimensional map in which the positions of the array and of the desk are depicted as reference. The maximum of the map, highlighted by the circle, is produced by constructive interference of the contributions due to all the reflections. Therefore, the loudspeaker position is clearly detected. Now the loudspeaker is in a different position, and we get a different pattern of impulse responses and a new acoustic map. Now I rotate the loudspeaker toward the left wall. The source is localized again in the same position, but this time the contribution from the left wall is much more evident. If the source is not controlled, for example a loudspeaker emitting an unknown signal or a person speaking, we cannot directly measure the impulse responses. In this case, we can only estimate mutual delays between direct and reflected wavefront arrivals. In order to estimate such delays, we use the generalized cross-correlation phase transform, that, although it is a non-linear operator, provides an approximation of the cross-correlation between impulse responses along the array. Here we have an example of the phase transform measured along the array, and we can see how it evolves when moving from one side to the other of the array. This is the graphical representation of the phase transform along the array, using the first microphone as reference for all the other channels. Again, we can match the resulting pattern with the one produced by an image method simulation and obtain an acoustic map which we call MultiPath Global Coherence Field. Information is here weaker than in the impulse response patterns, but with wideband sources as speech and the accumulation of phase information over analysis windows of a few seconds, the phase transform patterns are clear enough for source localization. Also in this map, the maximum peak corresponds to the source position. It is interesting to observe that the partial matches of measured and simulated patterns produce a sort of tracks along the path followed by various reflections. In particular, the reflection points are emphasized as a consequence of the fact that they are also mirror images of themselves in the image method simulation. Now I am speaking with my head oriented toward the right wall, so producing a strong reflection on that surface. The phase information in this case is quite weak, but the produced acoustic map is good enough to localize correctly the acoustic source. The maps we have seen are produced using the linear array with 64 microphones. This helps in analyzing with fine detail the multiple wavefront propagating in the room, and the resulting acoustic maps are quite detailed due to the redundancy of information collected by so many channels. However, the source localization can be achieved also if we reduce the number of channels. This is the acoustic map obtained if we only use 4 microphones, that is, 1 microphone out of 16 along the array. The map is more noisy, but still the localization was successful. In principle, the localization can be performed also in a 3D space, provided that suitable reflections from the floor and the ceiling are present.